I recently set my Year 12 students a challenge, which I hadn't worked the solution out to before I set it, and so I kind of messed up a little bit during the lesson. So here's a video to clear up what was going on. In the question, we had a track which was a loop like this. It's a circular loop, as badly as I've drawn it, a circular loop with a diameter of 50 meters, and it's a road. And we are in a vehicle, a car, with a mass of 1,000 kilograms, 1 metric ton, which is going to drive into this loop all the way around and out the other end. And so the challenge was, when driving at the slowest possible speed around this ramp, what must be the component of acceleration parallel to the ramp at B? Now, that's quite a challenging question, it really is. So initially you could say, well, the component of acceleration at B that's parallel to the ramp must be 0 if we are in constant circular motion. However, what I meant, and I should have been a bit clearer about this, is I want to know the component of acceleration parallel to the ramp at B caused by the engine. In other words, my foot on the throttle of my car, how far down am I going to have to push it? How much work is my engine going to have to do? How much force is my engine going to have to provide at B? So we're coming in our car from the bottom left, driving around, and then coming out at the bottom. And the challenge, if you remember, was traveling at the slowest possible speed. Now, my vision was that we could use this question as an example of mathematical modeling, and I'll come on to that in a little bit. So in order to answer the question, the first thing you have to do is figure out how fast you must be traveling at C, the lowest possible speed at C, to go all the way around. And so let's start assuming that we are coasting. So we are not providing any engine force at any point in this ascension, and in this descension, I think that's a word, you're not braking at any point. So we're going to be going in faster, slowing down, and then speeding up again. Now at C, the resultant force is going to be the centripetal force, acting towards the center. So at C, there's never going to be any braking or driving force from the engine anyway. There are two forces that could possibly act vertically at C. That would be the normal reaction force from the road and the weight of the car. Now, the slowest possible speed you can go around the ramp is when the normal reaction force at C is 0. If you go faster than that, then there's going to have to be a component of normal reaction force acting towards the center. If you want to go slower, then the normal reaction force at C is going to have to act outwards. And the only way to get that to happen is to have some glue on your tires or something, and that's not the situation we're talking about. So in order to calculate what the slowest possible speed is at C, what we use is this equation here. We say that the only force is weight, because the normal reaction force is 0, and that weight is the centripetal force. And we can cancel our m's and rearrange to get v as the subject, substitute in our 9.81 meters per second and our 25 meters, and we get 15.6 meters per second as the lowest possible speed that we can move around this ramp. Okay, well that's fine. We've now got the lowest possible speed. Now what a number of students did is consider what would happen if you were coasting all the way around. So there's no engine force all the way around, which remember that wasn't the question. But let's start from there. So if we are coasting all the way around, what do we have to do? Well, the first thing we have to do is consider how much energy there is in total. This is the easiest approach, how much energy there is in total. If this is a closed system, so we're not using our engine to transfer chemical potential energy into kinetic energy as we ascend, and we are not using our brakes to transfer kinetic energy into thermal energy as we descend, if this is a closed system and all the energy that the car has when it enters is the same amount of energy it has at every point in this circuit, in this journey, then at the very top we have the maximum amount of gravitational potential energy. So let's first of all calculate that, and then we can add that to the kinetic energy at the top. And then we can use that to compute what the speed must be here, which is what a lot of students did. So let's do that calculation. First of all, the gravitational potential energy at C. So that is going to be the mass multiplied by the field strength, multiplied by the diameter of this loop, because that's the same thing as the height of the vehicle at C. And when you do that calculation, you get, 490,500 joules. We're going to want to add that to the kinetic energy at C. And we've already calculated, this should say 15, we've already calculated the speed, 15.66 meters per second, the lowest speed that the car can have at C when coasting. And so the kinetic energy is going to be half times the mass times that speed squared. And there it is, 122,617.8 joules. So the total energy in our system is the sum of those two. So at B, we know that that is the total energy. And at A, and at D, and at E, and every other point, that is the total energy. So how do I work out how fast we're going at B? Well, to do that, I need to know what the kinetic energy is, which is going to be the difference between this total energy and the gravitational potential energy at B. So to calculate the gravitational potential energy at B, we need to do a little bit of trigonometry. Well, first of all, we've got the radius of this circle is 25 meters, but then we need to add a little bit onto that. And the bit we're adding on, this is a right-angled triangle I've sketched here, the bit we're adding on is the 25 meters multiplied by the sine of 45. That's that extra bit of height. So the height at B is 25, that's the radius of the circle, plus 25 sine 45, or 42 points, and there's far too many significant figures here. It's about 43 meters. So that is the height of the vehicle at B. We can use that to compute what the gravitational potential energy is at B. Mass times field strength times that height, and that's what we get. The kinetic energy is going to be, therefore, the difference between the total energy and the gravitational potential energy. This is just from total energy equals the sum of gravitational and kinetic energies, but rearranged to get the kinetic energy all by itself. And so we can substitute those numbers in, and we get a speed, if coasting, of 19.72 meters per second. If coasting. But that wasn't the question. A lot of students did manage to get to this number, but the question was, the point was I wanted to go all the way around this circle at the lowest possible speed. And the lowest possible speed we already calculated as 15.6 meters per second. Now, if we're going at the lowest possible speed, and we're not coasting, and that is the lowest possible speed, then the driving force from the engine and any braking force is not going to be zero. And that's where it gets a bit more tricky. So there are two approaches, and the approach I encouraged my students to do was to consider a bit of mathematical modelling. Now, if we're going at a constant speed, then we know that the tangential acceleration is going to be zero at every point around this circle. There will be an acceleration, a resultant acceleration toward the centre, that's the centripetal acceleration, but let us just consider the tangential acceleration, which will be zero. If that's the case, at every point on this ring, there is a gravitational field strength acting down, G, and G is equal to a component of acceleration due to gravity. So at D, gravity is going to try to accelerate us down at G, so our engine has to try to accelerate us up with the same magnitude, G. And at E, gravity is accelerating us down at G, so we're going to have to brake with our brakes trying to provide an acceleration up of the same magnitude of G. At C, there's no tangential component of acceleration at all. There isn't any, because we're going to be travelling at the same speed at C as if we were coasting. And that's the same situation at A. We're going to enter at that speed, and there's no source of tangential acceleration there. So what we essentially have is, if we consider positive to be the direction we are moving and negative to be the opposite direction, so we're looking at this scalar acceleration where negative is a deceleration, what we're going to get is at A, 0, at D, G, forwards, this is what the engine has to provide, at C, 0, and at E, negative G, is upwards, is the opposite direction to movement, that's what the brakes are going to have to provide. So I did a quick table. The reason why, by the way, the letters seem like they're in such a weird order is because when I laid out the question, I started with point A, B, and C, and only added D and E later as part of the explanation. So here's a quick table. We've got our angle, and we're measuring from 0 degrees, which is, as you can see indicated on this diagram, 0 degrees is here. And so we picked 4 points that we easily know about. At 0 degrees, we decided that we'd have to be accelerating in the direction of movement with a value equal to g from the engine in order to have an overall tangential acceleration of 0. The engine would have to try to accelerate at g. At c, it's 0. At e, which is 180 degrees, the other side of the circle, it's minus g, so we're going to have to be braking with the same acceleration the brakes are trying to provide as gravity is trying to provide in the opposite direction. And at A, it's 0. And what I wanted to encourage the students to do is not overcomplicate things, look at that pattern and see if they can think of a function that produces those results. And I've just got here the sign indicates forwards or backwards. So in terms of mathematical modelling, a very quick sketch of this data, of these data, where we've got g here and minus g here. We've got a point here at 0 degrees, which is g, then 0 at 90 degrees, negative g at 180 degrees, and then 0 at 270 degrees. And that kind of looks like a cosine to me. A cosine with an amplitude of g. A cosine with an amplitude of g. So AD is the driving acceleration, or it could be braking, it's just what the car is doing. That would be an equation that we've derived just by looking at the numbers, and when we plug our numbers in, we end up with 6.94 meters per square second. And then we could use that multiplied by the mass of the vehicle to compute what the driving force would have to be. How hard are you going to have to drive that car to go around it at a constant speed? At B, what would your driving force have to be? So that was actually quite straightforward. There's not a lot to go there. However, none of them didn't do that, and they tried to look at this more as a mechanics problem than a mathematical modelling problem, and that's okay. So let's look at it as a mechanics problem. And let's first of all draw the vectors, a free body diagram at B. If we draw a free body diagram at B, we end up looking like this, where the normal reaction force from the road is always going to be perpendicular to the driving force by virtue of the fact that this is a circle. The driving force can always be tangential, only be tangential, and the normal reaction force is always going to be normal. So those are always going to be 90 degrees to each other, and the weight is down. And in this particular case at B, the angle here is 45 degrees. So what do we do next? Well, we know that the centripetal force is the vector sum of these three vectors. And I've put a little arrow over the top to indicate that it's a vector sum. And I've defined these three vectors here. Driving force, that could be the braking force, it's just what the car is doing. Centripetal force and normal reaction force. Fine. Well, what we know is that the normal reaction force is always going to be in the same direction as the centripetal force. Always, always, always. So we can draw a diagram where we've got the weight and the driving force from the engine, and we know that these two arrows must, this mg arrow must start and the fd arrow must end along a line that produces a perpendicular to the fd arrow. That must be the case. And there is another force along that dotted line, which is the normal reaction force, which will not be equal in magnitude to the centripetal force. This is where I messed up, because the centripetal force would be that normal reaction force and the other two forces. So the normal reaction force is not the centripetal force. It's just one of the three forces that, when added together, make the centripetal force. Okay, well, now we've got a diagram. Even though, there's a normal force here which isn't the same magnitude, it doesn't matter. We know that this is an angle of 45 degrees, and we know this must all make a nice triangle, so we can use trigonometry. And we know that the driving force, therefore, has to be mg multiplied by the cosine of theta, because it's a right-angled triangle. We could plug our numbers in, and we get a driving force equal to this, which if we divide it by the mass, because of Newton's second law for constant mass, F equals ma, gives us a driving acceleration of 6.94 meters per square second, which is exactly what we got using mathematical modelling. A slightly quicker approach, mathematical modelling, I would say, because you just look at the numbers and just pick an equation based on the numbers. And again, that's the component of acceleration tangential to the road. Now, what you might want to do, that's the answer to the question, by the way. That was it. That's what I wanted. And you can get that either way, either by considering the force vectors or by simply mathematically modelling what the data is showing you. But we can extend this question further. We can look at the normal reaction force. Now, in everyday experience, if we are just standing where we are, the normal reaction force from the floor upwards on us will equal our weight. Well, you can't actually feel your weight. You cannot feel gravity acting on you. What you feel is the ground pushing you back up. You've got sensors in your feet. You've got sensors in your skin that detect pressure and can tell that you are standing. If you are in an aeroplane that falls from the sky, then what's going to happen is you're going to feel weightless. Of course you're not weightless, your weight is still acting, but what's happening is as you are falling, there's no support force on you, and so you have this feeling of weightlessness. So if we know what the support force, the normal reaction force on the car is, we can look at how weightless it is, if you like, what it feels like in terms of weightlessness. So I've done a quick calculation for that. What we've got here is that the centripetal force minus that normal reaction force is going to be equal to mg sine 45. So if we go back to this picture here, we know that this arrow here is going to have the centripetal force, which is in this direction, which is also going to have within it the normal reaction force. The normal reaction force acting down in this direction here. The normal reaction force add to these two vectors is the centripetal force. So I'll say that one more time. The centripetal force is this plus some normal reaction force. We said that before. The normal reaction force is in this direction, like that. So it's the same direction as the centripetal force. And this plus this is this length here, which is mg sine theta, mg sine 45. So what we can say is that mg sine 45 plus the normal reaction force is the centripetal force. Or another way of saying that is that mg sine 45 is the centripetal force minus the normal reaction force. And you can plug your numbers in. Now we know what the centripetal force is. We can calculate what that is. That's going to be mv squared over r. And we know what v is because we said we were travelling at the slowest possible speed around this ramp. So we substitute our numbers in and we get a centripetal force here. And so the difference between those two forces is that. That is the normal reaction force on the car at B. It's not the engine force. We've already done that bit. This is the normal reaction force. The engine force, if you recall, was about 6,936.7 newtons. That was the driving force from the engine that we would need. But this is the normal reaction force. It works out to be about 29.3% of the weight of the vehicle. So you would feel a bit lighter, 29.3% lighter, or so I should say 29.3% as light, as you normally do when you get to here. And you would feel completely weightless at the top. Well, the numbers check out. That makes sense. That all works. So that's really the answer to the question that I was asking. It's not laid out as very neatly, but there we go. That was the answer to the question that I was asking. And you can see that it was quite a lot of working to work through it vectorially, but you can just look at the accelerations in this circle, mathematically model it, and it's a little bit quicker to do it that way, giving you exactly the same result for the tangential component of acceleration that the engine or brakes must provide in order to travel around this circle at a constant speed. Hopefully that's been useful and cleared some things up. If not, play the video again.